In this next lesson about torque, we're going to find the net torque that acts on an object. So when we have multiple torques, we typically will make the counterclockwise torque positive and the clockwise torque negative. So in this sample problem, we want to calculate the applied torque on a disk from three different forces. And you can see they're each acting with a different magnitude of force, and they could also be at a different lever arm. So on a disk, the lever arm is going to be effectively the radius of the circle that it's acting through. So the distance from the center out to where the force is applied. Notice it's in centimeters, so we'll have to be sure that we convert to the correct units. So, which ones are counterclockwise torque? So, if we imagine that we're holding a pencil at the center and pushing in the same direction that the 28 Newton force is pushing, you can see that this is going to be a counterclockwise torque. So the 18 Newton force, if we do the same thing, hold a pencil as though it's at the center and push the bottom of it to the left, you can see this is going to be a clockwise torque. And if we do that to the 35 Newton force, you can see that's also going to be a clockwise torque. So to figure out the net torque that acts on an object, we are going to find all of the counterclockwise torques and then subtract all of the clockwise torques. So our counterclockwise torque had a lever arm of 24 centimeters. So remember, torque is RF sine theta. So my lever arm in this case was 0.24 meters times a force of 28 newtons. You can see the angle between them is 90. So sine of 90 goes to 1. Minus, I have two clockwise torques. So the 18 Newton force is also acting at a lever arm of 0.24 meters times a force of 18 newtons times the sine of 90 minus the 35 Newton torque, but that lever arm is this inner circle. So that's going to be 0.12 meters times 35 newtons times the sine of 90. So if I type all of that into my calculator, I get negative 1.8 Newton meters of torque. So what does the negative mean? The negative means that it's clockwise. So this is the same as saying 1.8 Newton meters clockwise. That's going to be the net torque from all three of these forces. In the next example, I want to calculate the net torque about the axle of the wheel, but now it's telling me that friction will oppose the rotation, oppose the motion. And it tells me the magnitude of friction is 0.60 Newton meters. So, if my net torque from the three forces is clockwise, in order for friction to oppose it, friction has to act counterclockwise. So in this scenario, I have net torque equals, we'll call our torque from above the applied torque because it was from the 3 applied forces. Okay. And so we'll say the net torque, now that there's friction, is going to be T applied plus the torque from friction. And we don't have to worry about subtracting because the signs will take care of that. So our applied torque was negative 1.8 Newton meters of torque. Because our friction is opposing a clockwise motion, our friction is going to be positive 0.6 Newton meters because it will be counterclockwise. And so you can see that when we add those together, we get negative 1.2 Newton meters, or that means 1.2 Newton meters clockwise. Now we're going to look at applying torques to a uniform beam. So you can just imagine a straight rod. Now we need to pay attention to the pivot point. Okay, so we're looking for the net torque on this 2 meter long rod or uniform beam about point C. So point C is our axis of rotation. So if you take your pencil and you hold it at point C, and then you exert a force that matches the direction of each of these forces, it helps you to determine if it's a clockwise or a counterclockwise torque. So holding a pencil in the middle, just like point C, and then I push on the top of the pencil with my finger up and to the right, just as the 56 Newton force is, I can see that causes a rotation that is clockwise. I then come down to point C, which is the axis of rotation. And if I exert a force on point C up and to the left, notice it's not going to rotate. I'm exerting the force at the axis of rotation. So no torque will be exerted here. In terms of the equation, the lever arm is 0. So because the lever arm is 0, there's no torque as a result of the 65 Newton force. The 58 Newton force, again holding the pencil in the middle, pushing down and to the right in the same direction as the 52 Newton force, you can see that this is going to be a counterclockwise torque. So now I have to figure out the net torque based on these 3 forces. We already discussed the 65 Newton force won't be exerting a torque. So my net torque, remember this is RF sine theta. So it tells me it's a 2 meter long board. So for lever arm, I'm assuming it's 1 meter from top to C, 1 meter from C to the bottom. So my counterclockwise torque will be exerted at a lever arm of 1 meter times a force of 52 newtons times the sine of 58. And this is positive because it is counterclockwise. This is 65 Newton force does not exert a torque. So now I need to go to my clockwise torque, which is exerted by the 56 Newton force, also at a lever arm of 1 meter, times 56 newtons is the force, times the sine of 32. So I'm going to type that into my calculator and figure out what the net torque is. When I type that into my calculator, it tells me that I get a positive 14.42 Newton meter torque. And again, 14.42 Newton meters because it's positive. The net torque is in the counterclockwise direction. If we go down to part B, we have the exact same setup, the exact same forces. Okay, the difference though is now our axis of rotation is going to be about point P, so the bottom of this rod. So what effect does that have? You can see now that the lever arm on the 52 Newton force is 0. So the 52 Newton force is now no longer exerting a torque. So I'm going to take my pencil, I'm going to hold it vertically, and then I'm going to essentially mimic the two forces that are here. So first, holding my pencil at the bottom, I'm going to exert a force in the middle of the pencil, up and to the left in the direction of the 65 Newton force. I can see that that causes this to rotate counterclockwise. So this is going to be a counterclockwise torque. Now I'm going to test the 56 Newton force, holding it at the bottom, exerting a force at the top that's up and to the right. I can see this is going to exert a clockwise torque. So this will be a negative torque. This will be a positive torque. So now I have to plug it into my equation. So to figure out my net torque, I have to consider all of the different pieces. One other thing is going to be lever arm. So from the bottom, we know going up to the midpoint is 1 meter. And then we have another 1 meter to get to the top. So that means that the lever arm for the 56 Newton force is going to be the 2 meters. So net torque, we're going to start with the clockwise. So the clockwise torque exerted at point C is exerted at a lever arm of 1 meter. The force has a magnitude of 65 newtons, and it's exerted at an angle of 45 degrees. The clockwise torque I have to subtract. The clockwise torque is exerted at a distance or a lever arm of 2 meters from the axis of rotation point P. The force has a magnitude of 56 newtons, and the angle is 32 degrees. When I type that into my calculator, I get a value of negative 13.39 Newton meters. The negative indicates the clockwise direction, so this is saying 13.39 Newton meters clockwise.